see the numbers climbing up still. I've had a question asking whether slides will be made available after the call. Yes, yeah, we can do that. Yeah, okay, I see the numbers are climbing up. I'll just get us set up before we get going. I'll give it another couple of minutes. Okay, I think the number's starting to stabilize. So I think let's make a start. Okay, so hello everyone who has joined us. Welcome to this presentation looking at net zero aviation in a UK context, which is taking place as part of the Cambridge Festival. So we're all based in the Department of Chemical Engineering and Biotechnology. Just before we get going, we'll just do a quick kind of round the table introducing everyone. So I'm George Fulham. I'm a PhD student in the department with the Energy Reaction and Carriers group, and I'm doing a PhD which is looking at how we can potentially upgrade CO2 to jet fuel. So I'll hand over to Paula, do a little introduction.
Great. Paula here, also a PhD student, and I'm doing research on hydrogen technology, also in the Energy Reactions and Carriers group.
Hi, I'm Mark. I'm a PhD student in the Department of Chemistry, but I used to be in the Department of Chemical Engineering and Biotechnology, and I'm in Professor Stuart Clark's group in the Chemistry Department.
Excellent. Right. I think without any further ado, let's get going. So what are we going to cover today? So we're going to give a brief overview of kind of the current situation and kind of the way things lie, give an overview of kind of the options that people kind of propose of potentially tackling aviation decarbonisation. And then we're going to kind of do a bit of a deep dive on kind of the three of the ones that get most talked about in the press and kind of giving an idea of some of the kind of pitfalls and advantages of each of them. And then we'll draw out some key conclusions from this all. So the current situation. So those of you who kind of pay attention to kind of this stuff in the news, we'll see there's a lot of interest at the moment from industry and government in trying to get to net zero aviation. And now there's very diverging opinions in this. Some people are very much backed a horse that they think are going to win this race. Others are a lot more agnostic, and others are outright skeptical, as some of these headlines show, about the possibility of reaching net zero aviation. So the plan today is basically trying to give an overview to try and maybe place some of these headlines in some context and give an idea of kind of the extent to which people are maybe playing with the truth or potentially being overly pessimistic potentially. So hopefully that's the aim of today, to give people a bit of a grounding in this all. So some figures to place this all in context. So globally, we use around 10 tons of jet fuel every second, which is a phenomenal quantity. The UK uses about 0.3 tons a second, so marginal in the global scheme of things. But when we compare that relative to our population, it is a very sizable number for how small we are as a population as a fraction of the globe. So let's have a look at that per person. So we use 100 billion gallons of fuel a year. That is equivalent on an energy basis to 500 kilowatt hours per person globally. So anyone with an electricity meter will be familiar with the kilowatt hours a unit. To place that in context, effectively, if you had a light bulb in your house and you left it on all day, that would use about 1 kilowatt hour of electricity. So globally, we're using about 500 kilowatt hours per person of jet fuel. So that's the equivalent of leaving 500 light bulbs on for one day. On the UK, because we're kind of a bit of an edge case and we're a fairly small island nation, which is obviously fairly economically developed, we end up being at the point of 2,000 kilowatt hours per person, so 4 times the global equivalent. So that is the equivalent of every person in the UK having 2,000 light bulbs on for one day in terms of energy consumption. Now, what did this correlate with in terms of a warming effect? So the oft quoted figure is this 2 to 3% of global CO2. However, as we'll elaborate upon later, that's only really a fraction of the picture because aviation causes warming in other ways. And so it's estimated that this could actually be 4 to 8% of the actual total warming impact. Now, for the UK, aviation is about 7% of our CO2 emissions and carbon footprint, but it could be as high as 20% of our actual warming impact. Now, as we consider every industry around starting to decarbonize the electricity grid, decarbonize road and rail, then this fraction is only going to grow. And then if we couple that with increased demand for aviation by 2050, we could be as much as 3 to 4 times higher by 2050. This 2 to 3% value is only going to grow and is going to become increasingly pressing as something to tackle. So where does all the jet fuel we use go? So numbers are available for the UK, which we can kind of use to give a breakdown of how we consume jet fuel. And so we use about 15% of our jet fuel to do short haul, 22% to do medium haul, and 50% to do long haul. So what do these 3 things mean? So on a map, short haul is a flight less than around 2 hours. So this is around kind of London to the south of France, for example. You then got medium haul. So this would be kind of London to Istanbul. And then you've got long haul, which is anything greater. So this is anywhere from London to New York, around 7 hours, to the kind of mega long haul London to Singapore stuff, for example. So how does aviation actually cause warming? So as we've alluded to earlier, CO2 is only part of the picture. So we're all happy with the idea that CO2 is going to be produced by burning fuel. However, we will also form water when we burn fuel. And this can lead to contrails, which are the kind of clouds we see coming out the back of planes. And this is where water effectively condenses and can form clouds which can last for anywhere from hours to days, potentially, depending on where they're released on the Earth and at what time of day. Now, the effect of both of these is to effectively reflect heat back to Earth and cause a warming effect, to put it simply. So the key things to take away from this kind of introduction are that genuine aviation is really going to need to tackle this long haul travel, because about 60% of the jet fuel we use in the UK is for traveling long haul. So that is the bulk of where we really need to direct our efforts. And in considering how we can decarbonize aviation and achieve sustainable green aviation, considering greenhouse gases is only really part of the picture. We need to consider both greenhouse gases and contrails. So how can we go about achieving green aviation? So some of the options people put forward are we can change our habits. We can fly less and use trains more. And this seems like a very sensible idea for doing kind of hops domestically or going across the channel potentially. We can legislate, so we can try and tax flights, because I mean, clearly a state of affairs now where I could fly to Rome for £20, but it costs me £60 to go to Manchester on the train, is not a sustainable state of affairs, and we should certainly look at addressing that. And then we can try and improve efficiency of aircraft, so we can try and make them burn fuel more efficiently. However, these 3 things are never going to be enough to actually get us to net zero. Changing habits. We looked at that graph before, which showed that we use of order 20% of our jet fuel to fly short haul. If we consider what we can do potentially with rail around Europe, we reckon you could maybe reduce fuel usage by about 25% with kind of shifting to trains. Legislation. People are still going to fly regardless. There will always be people, regardless of how prohibitive we make the expenses, and people are still going to want to fly to Australia and do these kind of mega long haul things, which planes are unfortunately great at doing. Improving efficiency. So we can try and make planes more efficient, but again, this is at best going to be 20–30% reduction in fuel consumption. So realistically, green aviation is going to need alternative ways of fueling aviation. So liquid hydrogen is one that gets talked about a lot. Alternatively, we could maybe use batteries. Or we could do sustainable aviation fuel, also known as SAF. So this is effectively stuff that looks like kerosene, but we make it in a way that's not reliant on fossil fuels. So some terminology to kind of give us a grounding when people talk about fuel production. So there's green production, which is defined as anything made from renewables. So this could be from renewable crops or potentially from renewable energy, so solar or wind. We've then got blue route. So these are ones that use fossil fuels. However, we're theoretically capturing the carbon en route, but we need to be very careful to ensure that this carbon capture is happening properly and is actually being stored in a kind of secure manner. And then we've got grey, which is kind of old-fashioned with fossil fuels, dirty, releasing CO2 without any attempt to kind of make capture. So the real thing to kind of ground ourselves in the problem of considering different fuels is there's a fundamental trade-off between kind of how easy they are to make and how easy they are to actually use on a plane. So we've got jet fuel down here, which is pretty easy to make. We can kind of refine some crude oil and then send that to an airport, put it on a plane. And it's obviously super easy to use on planes because they've been optimized for decades to use this stuff. So they're in a very good position to use it. We've then got our sustainable aviation fuels, or SAFs, which, as we'll touch on later, can be made via a variety of different routes, all of which are really quite challenging. However, they end up making something that looks quite a lot like kerosene, so they're quite easy to use on current planes. We've then got our hydrogen routes. So these are quite challenging to make, and they provide some substantial design challenges for aircraft. We're going to need brand new aircraft to handle these things. Liquid hydrogen is at minus 250 degrees. So we need insulation. We need really kind of fancy tanks. There's a lot of design challenges going on here. We've then got batteries, which are pretty difficult to make, but not super hard. I mean, we kind of know how to make batteries. However, using them on planes requires electric aircraft. So this is, again, quite substantial design challenges. And then we've got alcohol and vegetable oils, other ones that people talk about. So anyone who uses a car and is familiar with the E10 transition is aware of the fact that ethanol can be used within fuels, which is obviously an alcohol. However, there are going to be issues with using alcohols on planes. That it's not a simple drop it in at 100%, use alcohol in jets. There's going to be a substantial design challenges. And then there's vegetable oil. So we can make sustainable aviation fuel from vegetable oil. And so some people have asked, well, why not just use vegetable oil? Why not cut out all this fat to turn it into fuel? And now vegetable is obviously really easy to make. We can crush some rapeseed and extract some oil. However, you're going to have kind of inherent variability there, and there's a lot of design challenges with kind of accounting for that variability in planes and getting it to kind of burn clean. And so this is not a trivial thing to do by any stretch. So sustainable aviation is going to require new fuels, almost certainly. And in kind of understanding different fuels, the crux of the problem is this trade-off between how easy they are to make and how easy they are to use. So I'll hand over to Paola now to give us a bit of an insight on some hydrogen production.
Great, thank you, George. Okay, let's focus on hydrogen as an alternative fuel, as one of our options. The hydrogen is a fantastic molecule that we have available. It is one of the most investigated molecules in the world. It's the simplest element that we learn about in our chemistry class, and is the most abundant element in the universe. So when we say that hydrogen is great, we're saying that it's a promising energy carrier and feedstock. And what we mean by that is that we're referring to hydrogen's ability to transport energy from one place to another, so from one form to another. Hydrogen we can make from water, from fossil fuels, or from biomass. And once we have made it, which is a complex process, once it is made, we can actually use it in a lot of parts of the energy sector. So it can do a lot of things for us because of this high energy content per unit mass that hydrogen has. So hydrogen is the one fuel that we have that has the highest energy content per mass, and it's about 3 times that of conventional fuel or of gasoline or kerosene that we use. So for context, let's say the sun is mostly made out of hydrogen gas, and when this hydrogen gas goes through fusion, that's how the sun releases all of this huge amount of energy because of this awesome property that hydrogen has. So hydrogen we can use on an airplane for propulsion in 2 different ways. So we can either use it via chemical conversion in a hydrogen combustion engine, or we can do it via electrochemical conversion in fuel cells. Sorry, my computer is doing a weird thing. Great. Both of these technologies are going to require a new propulsion system based on hydrogen. And this is going to require redesigning our airplanes. And it is also going to translate in reconfiguring our airports and rethinking how our distribution networks operate. However, if we make this thing work, we are looking at a fuel that virtually produces no carbon dioxide, even though we still have this question about whether or not we're making emissions better or worse because of this contrail issue that George talked about. So hydrogen propulsion is going to release no carbon dioxide. However, it is going to have a water vapor byproduct. And we still don't understand how this warming up effect is going to happen because of this water vapor. If we figure out either one of these technologies, we are going to have to look at the challenges that exist in the central supply chain of this liquid hydrogen and in the infrastructure to be using this liquid hydrogen. So I'll break that down for you. So in the airport challenge, we're looking at two different sections. One of them has to deal with the production and the other one has to do with the handling of this liquid hydrogen supply. So focusing first on the production of hydrogen. If we are going to produce green hydrogen, which we should, if we want to produce a hydrogen that has the least environmental impact, it produces the least emissions, we're using the least resources, and we're using those resources in the most effective way, then we're looking at producing hydrogen via electrolysis. So electrolysis is the process by which we break down water molecules into hydrogen gas and oxygen. That is the one technology that we have available right now that produces hydrogen in the most efficient way. Even though this is the best option that we have, this process is very, very, very high. It's a very high energy consumption process. So we are using a lot of energy into electrolysis, and at the same time, it has a very low energy efficiency. So what I mean by that is that we're putting a lot of energy into producing this hydrogen gas, and it really doesn't make up for the amount of energy that we end up having in hydrogen as an energy carrier. So a lot of electricity needed on this side, which means that we also need renewable energy production at a large scale. And we need that renewable energy to be readily available so that we can make sure that we're producing hydrogen via electrolysis in a continuous way to support such a large supply chain. And there are a lot of emerging technologies in this area of electrolysis, but again, they're under development. They're not ready, very ready. So this is what we're looking at. This is the picture in production. Once we've produced the hydrogen gas, then we have to liquefy hydrogen. Why do we have to liquefy hydrogen? Hydrogen gas occupies a lot of space. It has a very, very, very low density, which means that to be able to handle this hydrogen, we need to make it occupy less space. And to do that, we need to make it into a liquid. So we need to use hydrogen in its liquid phase. The issue is that hydrogen liquefies at negative 250 degrees Celsius, and that is very cold. So on Earth, the coldest place that we have on Earth is Antarctica, which is at minus 90 degrees Celsius. So this is a lot colder than that. So very, 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 very cold temperatures, which means that we need a lot of energy to make this happen. We need very clever cycles so that this liquefaction process can happen. And we are looking at a fuel that has, we're looking at a fuel with a cost of which 40 to 50% of that cost is associated only to this capital cost, this infrastructure cost that we're going to need to make this process. So once we've liquefied and we have the hydrogen in its liquid form, we have to transport it, and we need to think about how we're fueling this airplane. So because of these low temperatures that we're dealing with, then we have to make sure that our entire distribution network, so the pipelines, the vessels that we're using, the tanks that we're using where we're putting the hydrogen, the valves, all of these things are going to have to be made of materials that are resistant to these low temperatures, and that they can deal with the wear and tear of using this liquid hydrogen. And we need to think about logistically, how are we putting this liquid hydrogen from the liquefaction plant 2 tanks if we are transporting it by road transport to the airplane itself. So we need to rethink a lot of things. We cannot be using the infrastructure that we have right now because it cannot support it. So even though hydrogen is fabulous, very, very difficult to make and very, very difficult to use. So I want to illustrate this point by looking at a case study in Heathrow, for example. So take a look at Heathrow International Airport in London. So in Heathrow, we are looking at about 190 million kilowatt hours in fuel used per day. A lot of energy, which translates to 6,000 tons per day of liquid hydrogen. If we are transporting this liquid hydrogen, we've made it, everything's good, we've processed it, we've liquefied it. If we're looking at one truck transporting 4 tons of liquid hydrogen, or this would be the equivalent to about 10 tons times 25 carriages in one train. This would translate to 60 trucks of liquid hydrogen arriving at Heathrow International Airport per hour. So this is a lot of trucks, and it's a lot of traffic going to Heathrow. So even if we figure this out and this works, and there's still the question here of whether we are really reducing emissions or not, because then we're increasing the CO2 emissions coming to Heathrow if these trucks are operating conventionally. And we are making green hydrogen via electrolysis, and we're using a very optimistic case of a low energy consumption, the lowest one that we have available via this technology. And this electricity is coming from solar panels. So we're looking at solar energy to make this green hydrogen. Then we need at least 4 times the area of Heathrow International Airport in solar panels only to make this happen. So this is a lot of energy, a lot of trucks arriving at Heathrow, and a lot of land that is dedicated to only powering these airplanes from Heathrow. So in context, this is a lot that we're talking about, and we're not ready to actually be supplying this liquid hydrogen in this way. So it's very difficult. So the main takeaways with liquid hydrogen is that it is fabulous. It could be fabulous. It's very difficult to make. We're requiring a totally new aircraft to be used. We need to look at production and distribution of liquid hydrogen, which is very challenging. And a lot of research needs to be done in this area. So here in Cambridge, we are looking at hydrogen research focusing on precisely this production and distribution of liquid hydrogen. So how can we make this more energy efficient and in the most environmentally conscious way, and looking at other ways of making hydrogen that is not via electrolysis to see what happens if we totally rethink the way in which we are producing this hydrogen gas.
Thanks, Paula. So now let's take a look at one of the other options that gets talked about and have a look at some batteries and whether they could be used for planes. So when we're thinking about designing a battery-powered plane, one of the most important things we have to look at is how much power we require, so how much energy the batteries are able to deliver every second in order to take off and then climb. And planes are very heavy, and so it takes a lot of power to lift the plane off the ground. And that means we have to have sufficient power available from our batteries to get the plane off the ground, both at the start of the flight and also potentially at the end of the flight as well, where if you have to abort a landing and do a go around, you need to have enough power available again at the end of the flight. And that means you need a lot of batteries, and those batteries are very heavy. They're so heavy that actually the structural strength of the plane becomes a serious limit on how many batteries we can put into the plane to provide that power and energy. So if we look at how far a battery-powered plane could go with the current technology we have available to us today, if we take a pessimistic case, the plane would not be able to exceed the sort of mandatory safety reserve range that you have. So as soon as you took off, the safety regulations would effectively say you have to land. So that doesn't really work very well. If we take a more optimistic look, then you could get a bit further. But as you can see on the little map on the right-hand side, we're talking about, maybe just about being able to make it from London to Calais. Really not very far at all to be useful for tackling certainly that long-range problem that we've identified as being key. So if we look towards the future, then things get a bit better. You can make it from London to Paris. But again, we're still saying, we can get from London to Paris in that optimistic case. But again, we're still saying that we're not getting anywhere near tackling that long range problem, which we say is key to decarbonisation of aviation. So something we might think about as well when we're talking about these is around how we charge our batteries at the airport. And charging your electric car, if you have one, takes a fair amount of time. The batteries for a plane are much bigger, and they take correspondingly a much longer time to charge as well, which leads to long turnaround times at airports, which means that you need more planes to achieve the same capacity, which is more carbon emissions, and so on and so forth. So instead of charging the batteries on the planes, we might look at taking the batteries off the planes and loading new batteries into the planes. But normally that means that you have more weight associated with the infrastructure for that loading and unloading on the planes, which makes the planes heavier, which shrinks their range. So there's a trade-off there. Now, if you have an electric car, you will know that the range of your electric car gets shorter over its lifespan. That's because the batteries degrade as they get used multiple times. And this would happen with plane batteries too. And so the range of the plane would shrink over the lifetime of the plane. And there's a serious question as to what you do with the batteries at the end, whether you could use them in a different type of application, for instance, transferring them over to being used in cars, or whether you can do recycling, which is an area of current research and very important. And then finally, there is a question with these batteries about how sustainably they can be produced. There's a question about mineral availability for the crucial minerals like lithium and cobalt that go into these batteries, and whether there's enough of them available to produce lots of these battery-powered planes. And then, as there is with electric cars, there are questions around the ethics of where these minerals come from and how they're extracted in different places in the world. So perhaps a different way of thinking about batteries that might be more promising is to look at using them in conjunction with fuel cells on airplanes. Now, fuel cells have very low power densities compared to the batteries. And so that means that we could use the batteries to assist with that big spurt of power that you require at the start of the flight to get the plane off the ground. And you have both the battery and the fuel cell supplying power to the motors to move the plane. And then, as we said before, one of the key aspects about battery planes is the need to have enough power at the end of the flight as well. And you could do that by having the fuel cells provide a charge to the batteries over the period of the flight, such that when you're coming into land, you've charged up the batteries and can use that if you need to do a go around, which also helps you avoid long charging times when you're on the ground. But it's worth noting here that fuel cells would require complete aircraft redesign and a lot of technological research, as do the batteries. So this is a big research requirement to make this a possible reality in the future. So the key points for battery planes are that there are severe range limitations that are unlikely to go away in the next 25 years. We have to be careful about the sustainability of the batteries and the minerals that are required for them. But in the future, we could see hybrids with fuel cells being promising, but that's a long way off.
And so finally, I'm just going to give an overview of some SAF. So we've gone through hydrogen and we've gone through batteries and seen that they've got promise, but they're potentially disadvantageous and difficult. And so that's motivated quite a few people to go, well, let's just try and use some kerosene, but let's try and make it without fossil fuels. And so how can we make kerosene without fossil fuels to make sustainable aviation fuel, or SAF? So there's many different routes in which we can do this. So one is that we can take some bio oils. So we could get this from essentially algae or from oily crops, and we can then upgrade this to a jet fuel-like substance at the end. Or we can do something called alcohol to jet. So here we can take some crops and we can turn these into alcohol, potentially by fermentation or potentially by some more exotic means. And then we can upgrade this alcohol to jet fuel. And this is something that British Airways has partnered with the company to get involved in. And we could do something called gas to liquid, whereby we take potentially some waste municipally, so from landfill, or potentially waste from agricultural residues, and we can gasify these, which is where we effectively subject them to high temperature and pressure, such that we can basically yield a gas mixture from them. And we can then do some pretty clever chemistry with that gas mixture to then upgrade it to something that looks like kerosene jet fuel. Or finally, we can do power to liquid, whereby we take some carbon dioxide, and we'll go through some of the ways in which we might source this carbon dioxide later. We can combine that with renewably powered electrolysis to make hydrogen, and through combining hydrogen and CO2, we can make a similar gas mixture to that which we get in the gas to liquid case, and then we can do basically the similar clever chemistry to upgrade that to jet fuel. So with the first three of these, where we're using crops and agriculture, then there's kind of an inherent trade-off there between kind of competing for food versus fuel, which is kind of a long-running debate in this kind of biofuel debate. So if we think about the UK context, we've run some numbers and have a look at roughly how much land you're going to need. So in the UK context, the land required for upgrading biofuels, you would need a land area roughly about half the UK turned into oily crops. And that's just for aviation. Half the UK with oily crops being grown. So clearly this is not very tractable as something to do. For alcohols getting gas to liquid, you're talking about 80% if we're using crops and agriculture. So this is even harder. And so this has led people to think about power to liquid, whereby if we're using CO2 and renewable electricity, we don't have this same kind of hefty land requirement. And so let's do a bit of a deeper dive on how power to liquid actually works. So power to liquid, also known as PTL, we do some water electrolysis, as Paola discussed earlier, to make some hydrogen. And then we can get some CO2. Now, we can source CO2 from a number of ways. So one is we could burn some biomass. And so this is what the Drax power plant does at the moment. And then we could try and capture that CO2, so we then got a CO2 stream we can do some stuff with. Or we could go to an industrial source. So we could go to a steel mill or a cement production plant and take some CO2 from there. However, we've got to be really careful with the actual net zero credentials of doing this. So if I take CO2 from a cement plant and convert that into jet fuel, which is then going to be burnt, effectively all I'm doing is shifting CO2 emissions from your cement mill to the back of a plane. I'm not actually making it net zero. I'm effectively just getting almost two uses for the same emissions. So it's something worth looking at, but it's not actually going to get you straight to net zero. So we've got to be really careful with the neutrality credentials of that. And then finally, we've got direct air capture. So this is where we literally take CO2 out of the air. And so this seems like a great idea. However, we've got to bear in mind that even though CO2 is at dangerous levels in the atmosphere and levels that we need to obviously tackle, it still is around 400 parts per million. Whereas if you're looking at industrial sources, your CO2 is going to be tens of thousands or hundreds of thousands parts per million. And so you're dealing with a much more dilute stream of CO2 in air. And so therefore you need to put a lot more effort into basically get that CO2 stream. But once we've got this CO2 and we've got the hydrogen we just mentioned from electrolysis, we can put these into a chemical plant and do some quite complicated chemistry. So we can do some reversible gas shift where we basically make a gas mixture we can then do some reactions with, and then we do a process known as Fischer-Tropsch to turn that into jet fuel. Now, so this doesn't have the land requirement of the ones we went over previously to the same extent. However, we're going to need a chunky amount of power. So in the UK context, we reckon in a very generous case, you maybe need to increase the UK electricity generation by 1.5 times for UK aviation alone. And now we bear in mind that everything else is starting to electrify, so electric cars, then there's going to be a huge demand on electricity there, and aviation is going to be sucking up a lot of electricity there. And in the worst case, we might need to increase it by 4 times for aviation alone. So even though you don't have quite the same demand on land, although with biomass combustion, you are going to get into issues with using land, you then also got a huge issue with how much electricity this process actually requires. So sustainable aviation fuels, or SAFs, are probably the hardest fuel we can make, but the easiest to use because they look the most like kerosene. There are many ways we can make SAFs. However, out of these, power to liquid is probably most likely to achieve net zero, but we've got to be really careful with how the carbon accounting is done on people claiming PTL can reach net zero. So what are the key conclusions we can draw out from what we've gone through today? So any option which cannot address long-haul aviation is not really a true solution in reaching net zero aviation. And of the solutions that are proposed, there are no easy solutions, and any solution is going to require huge change at the system level and a complete rethinking ultimately of how we go about fueling and operating aviation. So with that, I'll wrap up and welcome any questions. So either submit them via the Q&A in the webinar or on YouTube if you're watching from there.
There was one question on hydrogen by Joseph, and I just kind of put an answer there for people to read. But the question was, how many gallons of conventional fuel does Heathrow currently use on a daily basis? So that number that was on the slide, that was for jet fuel, and that was on an energy basis. I don't have the number for you in gallons right now.
I can. So
you got it.
So it uses 190 million kilowatt hours, and that's basically the energy content of jet fuel we require. What we did was we effectively said, assuming your energy demand doesn't go up when you switch to hydrogen, you would need that 6,000 tons per day of hydrogen. Now, with jet fuel, because it's got about 1/3 of that energy content, then that 6,000 tons is going to become about 18,000 tons. Yeah. Now, this makes the very generous assumption that effectively your energy demand doesn't go up when you're using hydrogen, but it might be that a hydrogen plane is heavier, or potentially it might burn less or it might burn more fuel, open question. And so potentially that value might even go up. Yeah, but about 3 times that 6,000 tons, so about 18,000 tons per day of jet fuel for hydrogen, for Heathrow even, sorry.
Second part of the question was, how does this 1 train per hour or 60 trucks per hour compare with the current delivery of jet fuel? So liquid hydrogen, if you're delivering the same amount of energy, has a density that is about 1/4 that of kerosene, for example. So then you will be looking at, if you are getting the jet fuel to the airport via truck, you're looking at 1/4 of those trucks, so about 15 trucks instead per hour. So it's significantly less than 60. And if you were actually producing hydrogen off-site and you were transporting hydrogen instead to be liquefied in the airport, which is an option that some people look at, then that number gets worse, because liquid hydrogen gas has a density that is about 1/848 times that of liquid hydrogen. So it's a lot more safe. That would be a lot more trucks.
I think the other thing to mention here is that for large airports, jet fuel is normally transported via a pipeline rather than by trucks, which makes it much sort of easier to handle those large volumes. But that hydrogen pipelines are a big challenge, particularly the idea of a liquid hydrogen pipeline is almost inconceivable with current technology.
We've had a question asking why the hydrogen needs to be liquefied. So the key thing here is, as Paula alluded to, is the fact that the volume of compressed hydrogen or gaseous hydrogen is much, much larger than liquid hydrogen. So effectively, you need a much bigger volume for the same energy of compressed hydrogen or gaseous hydrogen as you do liquid hydrogen. And now one of the solutions people propose to that is, what if we try and really, really pressurize this hydrogen? So we compress it loads. And so people talk about compressing it to about 700 bar. Now, to put that in context, that's about 350 times the pressure in your car tires. And so your car tires were pretty rigid. So imagine that times 350. And so therefore, to contain that, we need super, super strong tanks. And these tanks weigh a ton, to the point, well, tons actually, to be more specific. So the reality of this is that on your plane where you're carrying this compressed hydrogen, your tanks will take up around 90% of the mass of your fuel. So effectively, of all the mass that you can attribute to kind of being related to delivering fuel, about 90% of that is going to come from the actual tanks themselves, as opposed to anything that's actually providing actual energy. Whereas with hydrogen, this value can get up to about 70% potentially. And so therefore your weight, you're carrying a lot less dead weight of infrastructure for supporting the fuel on board. So that's why liquid hydrogen is really needed. And there's also safety questions about putting such high pressure hydrogen on planes. It really does, beg some questions about doing that. Had a question about using fuel cells and potentially whether they would produce water vapor or whether it could be stored on board and brought back to Earth at the end of the flight. So this is a really interesting question, and this links in what we were talking about with the hybrids. So fuel cells would produce water, which potentially you could store on board. The issue you would have then is that your plane would get heavier with time. And as your plane gets heavier, that means you're effectively going to burn more fuel to basically carry that extra weight. And so that would constrict how far you can fly. And so people often talk about effectively chucking the water out the back, at which point you're then into contrails issues. So what some people have thought about with the potential for hybrids is that effectively the hybrid allows you to toggle between whether you're using your battery or your fuel cell. And so the likelihood of forming contrails varies depending on where you're flying on Earth and at what time of day. And so the hybrid option potentially opens the scenario in which you're flying on fuel cells and releasing water at the back of your plane. And then the pilot could get a notification, or there might be some automated system that realizes the plane's in a contrail forming region and can then effectively switch to battery mode, where the plane then ceases to produce water to basically try and obviate the formation of contrails in that region. And so this could potentially be a very interesting way to kind of tackle the contrail problem, which battery fuel cell hybrids also open up.
Okay, so so we've got a question about conventional fuels and carbon capture in flight. So one of the advantages that you have of burning fuel when you fly is that as you fly, your plane gets lighter along the way. Whereas if you do carbon capture in flight, if you were to do it, your plane would get heavier as you flew. And that means that your range and efficiency of flight goes down considerably, which is the first thing to say. The second thing is that you would require a lot of heavy equipment on the plane in order to perform the carbon capture in flight. And so we looked at this and concluded that it was likely not to be particularly viable on planes.
Yeah, if I remember correctly, I think we said it, under a generous scenario, it may be reduced your range by a factor of a third, potentially, doing in situ carbon capture. And that's setting aside the potential technical difficulties, given the fact that ultimately the exhaust out of the back of the jet is kind of what pushes them forward. So it kind of also is going to require some kind of rethinking about how we actually do that. So it might require almost reforming the fuel before it's burned. And so again, a kind of a rethink of how we actually operate jet engines.
Yeah. So we have a question saying, why would a contrail of liquid vapor be an issue? George, do you want to?
It's effectively just the fact you've got these clouds of liquid vapor, which will, kind of condensed vapor, which will act to trap heat effectively. So the diagram we show, so if you've got vapor, water in the vapor form, it will act to trap and reflect heat to an extent. However, when this is then liquefied and forms these contrail clouds, that effect is kind of magnified, basically. That's why kind of having the liquid vapor clouds kind of particularly troublesome for contrails. The understanding of how and why contrails form is actually somewhat nascent still, and it's not something that people, and this is for kerosene. And so when we then kind of extrapolate this, then considering the contrail implications of alternative fuels, the level of uncertainty is humongous. Kind of the mechanisms through which they form. Some people have speculated that if you get kind of soot particles from your fuel, then this can help to promote the condensation of water and potentially make things worse. And so potentially you're not going to have kind of soot being formed from hydrogen engines. And so maybe the contrail issue is not so much of a problem. But again, there's a lot of speculation and not a lot of hard kind of data to actually provide authoritative answers on this.
Great.
Let me answer a question on the chat. So Oscar has a question for me, and then he has one for you, Mark. So Oscar asks, do you have any consideration of a supply chain design in terms of end-to-end risks and early adopter networks? So right now, in respect to end-to-end risks, is that so it's two things. We want to not have the infrastructure to produce hydrogen in this large amount, and at the same time, we don't have the demand of hydrogen in this amount. So we want to use it, and we can't make it, and we can't use it yet. So it would have to be a matter of making sure that we have an airplane that can work on this hydrogen, or alternatively, that we can drive the supply chain to this large demand via another sector. So using it in another application of hydrogen. It can be used in medicine, right? So they use it in like MRI applications and other sectors of on the medicine. You can use it to upgrade biofuels. So bio oil that you make from biomass, you can upgrade it, and you need to have a hydrogen for that. So in the more ways that we use hydrogen, then we can drive the supply chain. Assuming that then we have an airplane where we can put it. And then there's also the issue of, well, if we end up making all this hydrogen, is it going to be feasible to be making it to power not only aviation, but other things? So really we need a lot of collaboration, a lot of international collaboration really, and between institutions. And it has, the airplane at the very end of the supply chain has to do with early adopters. So there are institutions like Airbus, for example, right now, who has a airplane that runs on a modified gas combustion engine that runs on hydrogen, so combustion hydrogen with oxygen. And they are allegedly testing this airplane for this to work, so long haul airplanes this year. And George, I know you know more about early adopters right now at the moment.
In terms of people looking at hydrogen.
Yeah.
So
there's Airbus.
Yes, Airbus are talking about the 0E hydrogen. So they've really backed the hydrogen horse. And then Boeing seems to be pivoting more towards SAF. So on that first slide, there was that news that said Boeing committed to buy 2 million gallons of SAF. Now, ultimately, we compare that to the 100 billion gallons that the world uses annually. It's kind of dropping the ocean, but Boeing are very much backing SAF, it seems. Airbus are very on board, with hydrogen. And then there's also kind of some smaller startups. So there's Zero Avia, who I believe are looking at hydrogen fuel cell planes. There's a few kind of dynamic startups that are kind of looking at hydrogen aviation. But Airbus kind of the big player that are kind of really really backing hydrogen at the moment. We've had a question about how does the impacts of aviation compare to cars global warming. So I believe that transport globally accounts for about 30% of emissions. And then of that 30%, around 3/4, give or take, is from kind of cars, bus, trucks, and lorries. So we're talking about 3/4. So of all the kind of 22% comes from kind of road transport. So aviation is obviously smaller than that. However, you do kind of have this question of contrast, which is kind of unique to aviation, which then means kind of doing a like-for-like comparison becomes tricky. And then also you got the question that kind of people know what we're going to do for the road market. Kind of people are kind of saying we're going to electrify and go for kind of battery power, and then potentially maybe go for some kind of more exotic stuff for trucks and stuff. Whereas for aviation, the question is so much more open, and so yeah, that's kind of another thing to bear in mind.
We have a question saying, could you pipe seawater to Heathrow and then electrolyze that on site? Paula, do you maybe want to address that?
Yes, on anything that's on site, in my opinion, would be better than trying to transport a lot of things from place to place. Is that me?
Yeah, I suppose, so first of all, seawater, you have to clean it up.
Yes, I'm getting feedback from my own voice. That's why. Okay, it went away. That's good. Yes, anything that's on site, I think will be better, because then you're taking away the transportation issue. Also, there's another component of liquid hydrogen that if we're looking at transportation, especially over very long distances, then we have to be careful with it self-evaporating. So we might lose some liquefaction there. So I think if you can make an electrolysis plant big enough that is powered with a renewable energy source big enough that is at the same time coupled with a liquefaction plant that is big enough to power Heathrow, then yes, you could do that. And that would be very, very difficult, and also not as difficult as all the other options that we have. But sure, that's a good pitch for Heathrow Airport.
I think it's worth providing a scale, and you're effectively talking about an entire nuclear power plant's worth of electricity having to arrive at Heathrow to provide that facility. So you're talking about a lot of energy that you need to deliver to one place, and a big plant that you'd have to build.
Yeah, and then there's the question, the amount of kind of genuine and kind of understand kind of well-meaning and I think understandable pushback in out of a third runway at Heathrow. So the idea that they're then going to build a nuclear power plant there, and then all these solar panels, and then all this electrolysis equipment, I think is going to get a fair chunk of pushback. We've had an interesting question about ammonia for use on planes. Mark and I smart, we've had a lot of fun with ammonia in the context of aviation, memorably being asked to look at whether we could make ammonia not smell bad for use in aviation. So the question with ammonia kind of fundamentally comes down to the worries about NOx, so nitrogen oxide emissions, which is a potent greenhouse gas if you're burning that in jet engines. There's also a question about the actual speed at which your flame progresses ammonia, actually kind of the stability of it and how well that will actually operate within a turbine system. I believe Pratt & Whitney have done some work looking at ammonia turbine engines. But again, this is one of the points where the worry about if you had an ammonia leak is a very real one and a justifiable one. And then there's substantial technological challenges. I think for shipping, ammonia seems to be kind of the horse a lot of people's backing, and one for which I think you can make a good case for that. For planes, it's tricky. Some people have talked about using ammonia as a way to kind of overcome that difficulty of hydrogen transportation, the idea that you maybe convert hydrogen into ammonia, take it right to the airport, and then reconvert it to yield hydrogen close to the point of use. But again, this is just going to make it even more costly to make your hydrogen, because effectively you're having to pay to turn it into ammonia, then turn it back. So I think ammonia for aviation is is one I'm not that optimistic about. I think there's a lot of technological challenges, and I think even if they're overcome, I'm not sure to what extent it's actually that competitive with other ones. So in terms of the range it can attain, the actual range that ammonia could attain is actually still not great versus liquid hydrogen. It would struggle to kind of do the uber long haul stuff.
And I think part of that is down to, if you're talking about doing conversion on the plane, the weight of the catalyst and system that you need to convert it back from ammonia into hydrogen is currently prohibitive and would require some serious research, which some people are attempting to do and look into to do that. So you talk about a heavy goods vehicle, the weight of that matters less, because whereas in a plane, the amount of energy you require is strongly affected by the weight of the plane. So that's a key consideration.
And also with such a configuration, you would need to have a backup plan, right? So that you probably start with a hybrid plane. So again, the issue of the weight. Are you running a regular jet fuel plane with an additional entire system to produce and use that hydrogen? That's a lot of things to put on the plane. I think someone did a funny calculation, and they were like, if you did that, then your plane would carry your normal plane would carry 12 people, and then the rest would be just the airplane to be powered.
Yeah. So Mike has asked, has there been any modeling of passenger demand as we increase the costs of seats? It's certainly not something we've looked into. I think it's something that I think would be very difficult to get sort of honest answers out of people on if you were to conduct surveys and such like, because I don't think people know how they behave necessarily in that kind of scenario until they're presented with it. I suppose I would say that, in the 1980s, flying was considerably more expensive than it is now, and there was still substantial demand than back then as well, although less.
I had a question from Guy saying maybe the age of frequent recreational flights is over, and would that be so terrible? I think I would echo that. I think I think you hear a lot of people talking about the idea of battery planes being great for enabling kind of people to do short hops to London, Paris all the time. And I think that my answer to that would be there are these things called trains. They're really good. We should just use those to do that. I think the idea of trying to enable kind of short hop kind of tourist travel and enabling that with battery power is a marginal consideration. I think ultimately, people should be a lot more considerate about the fact if they're kind of jetting kind of long distances frequently. I mean, how necessary actually is that? And I think the pandemic has kind of put questions of that into sharp relief. Now, the extent to which lessons will actually be learned over a long time from that, the extent to which people kind of realize that potentially traveling long distance for a business meeting is unnecessary, it's kind of remains to be seen, I think.
Paula, there's a question for you on onboard hydrogen generation mechanisms from chemicals and then using that with fuel cells.
Yes, I haven't looked into it. Really not. Yes, I'm not an expert in that area. I think it would go back to the idea of your plane getting very heavy and needing a backup plan, so running a hybrid for a little bit. And I think the best thing to do, especially because you can use hydrogen not only on board for the propulsion, but because we're going to need it for many other things, then it will be easier to figure out getting the supply chain to work in a cost-effective way and in an efficient way, and in a reliable way, than starting to make planes that are going to generate hydrogen on site and be using it in that way. And with fuel cells, again, with fuel cells, we're looking at short haul, so not probably a good idea for tackling the long haul issue. But a good question.
Yeah. Okay. George, we have a couple of, yeah, thank you, Paula. We have a couple of questions about contrails. I wonder if you might want to address talk about some contrails.
So we've had some questions about the extent to which contrails should be worried about, say, versus clouds. I think the point to make is effectively in the same way that we kind of have natural CO2 cycles that occur in the atmosphere, effectively our impact from industrial activity to effectively disrupt that and kind of an extra thing kind of imposed on that, which kind of disturb what is a fairly kind of delicate equilibrium that kind of manages our climate. And we can kind of make a similar argument with contrails. We have kind of naturally forming clouds, but as soon as we then start introducing contrails on top of that, which can often be very widespread over hundreds of kilometers, we're effectively introducing another kind of perturbation, disturbance into what's a fairly delicate equilibrium, which is then kind of causing an additional warming effect over what would kind of be happening naturally. And so it's kind of this idea of kind of superimposing external effects. Is the best way I could kind of describe the impact of contrails.
I think the other thing to add here is that the science around contrails is very uncertain and new. I think it's fair to say, and the comparison to CO2 emissions in particular, and is very, very difficult to do. Effectively, contrails provide a sort of fixed warming effect, whereas CO2 provides a continuous warming effect. And so that comparison is very difficult to make. And in terms of comparing them, no one really has a good thick, sort of clearly established methodology for doing that. The other thing is the impact of them varies considerably according to the time of day. So during the daytime, the contrails do reflect light back into space, and that provides a cooling effect on the planet, which the clouds do as well. Whereas during the night, they only reflect light back to the surface, which is being radiated away from the Earth, and so only provide a warming effect. And it's all about that trade-off between what reflects light back to Earth and what reflects light into space, away from the Earth into space. Yeah, so it's a very difficult question and very complex.
And there's one last question about, that was a very good way of explaining it, Mark. Thank you. I understand that better now. There's a question about new safety issues because of all of this method. Yes, if we're not using, there are safety regulations and procedures to follow with just using regular jet fuel. If we use a different jet fuel, we're gonna have to rethink that as well. So yes, there's that. It's not impossible. We run arguably, we do arguably dangerous chemical processes all the time. We use them all the time, and we do it safely and we do it well. So I think as long as we know what we're doing and we are running our risks assessments the way that we need to, I don't think that would be the issue, safety issues.
I mean, and to elaborate, so with the SAFs, the sustainable aviation fuels, for safety reasons, there's a limit to how much you could actually currently blend those with current fuels. So current fuel contains a portion of aromatics. So these are the, so normally you have kind of straight hydrocarbons, and then alkanes are kind of the cyclic ones. And these are kind of what give petrol an odor, hence the term aromatics. Now you require 20% of these aromatics in kerosene you're going to put in a plane because these help with the seals on the aircraft to avoid fuel leakage. They basically cause them to swell so you don't get fuel leakage, which could obviously lead to forming a kind of vapor of fuel, which could potentially lead to severe issues on board aircraft from a safety perspective. So for safety reasons, you actually can't use wholesale replacement of sustainable aviation fuels at the moment. And so unless you can make ones that look a lot closer to what current aircraft have been built to operate. And the different SAF routes we make slightly different fuels. And so different ones of them are allowed to be blended to different extents. So the ones from bio oils can blend up to 50%, where some of the other ones, where they're from the gas liquid, can only be blended up to say 20, 30%. And so one of the areas of research we're looking at is alternative ways to make sustainable aviation fuels, which might be closer to what current planes can handle. And then you've also got the question of potentially just trying to redesign seals so they don't need these aromatics. Because I mean, ultimately, the design of aircraft has basically just been set according to what came out of crude, effectively. No one sat and kind of designed the optimum jet fuel 60 years ago and then started as a starting point. They effectively saw what came out of a refinery and went, well, this is kerosene, let's work with this. And then we've kind of optimized planes around that. Now, realistically, kind of achieving sustainable aviation is going to be a complete paradigm shift in the sense we need to kind of reorganize how we think about fueling aviation. Currently, aviation kind of taps off a pre-existing industry that's making this jet fuel from crude, whereas now they're actually going to have to take responsibility for the infrastructure and production of fuels that they use, and they're going to need to kind of recalibrate how planes are designed to kind of handle these new fuels. So it's kind of a complete paradigm shift. There's a bit of a tangent to the question, I confess. But in terms of hydrogen safety, there's obviously the risk of hydrogen explosions. If you have a leak on board, this is particularly prevalent if you're trying to move liquid hydrogen around your plane. So you can load liquid hydrogen on, and the question is, well, how do I get that to the engines? So one school of thought is the idea you basically let some of the hydrogen evaporate off, and then you then got a gas mixture of hydrogen you supply to the engines. Alternatively, some people talk about trying to supply it as liquid right up until the point of the engine. And now if you're doing that, that opens the risk of hydrogen leaks throughout the aircraft over the kind of the piping infrastructure. And again, how do you build this piping? And then you've got the risk of potentially forming an explosive atmosphere of hydrogen. Now, unfortunately, if there's an explosion on a plane midair, it's not going to end well, kind of regardless of what fuel you've got on board. But there are certainly pertinent questions for hydrogen that are not trivial, and certainly should be looked at in terms of how we handle this. Again, if we're getting to the idea of doing hydrogen being made near airports, if a plane has an issue on landing and hits one of these hydrogen production facilities near an airport, it would be a catastrophe. So you've then got there's all sorts of these issues that really need to be thought about with a lot of care. Yeah.
Okay, we've run slightly over, so I think we probably need to draw to a close now. Thank you all for your questions. It's been really interesting to hear from you, and I hope that you've enjoyed hearing from us, and all of the other events in the Cambridge Festival. Yeah, thank you so much.
Right. Take care.
Thanks, everybody.